Okay, so an introduction to limits. You have most likely, if you took courses at FLCC, you've heard mention of limits in college algebra, maybe pre-calc. Um, but here we're going to really kind of dive in a little bit deeper into this idea because limits underpin all of calculus. They're what's called the underpinning of calculus. Oftentimes they're in the background. Sometimes they're the key to solving a complicated problem. But what they definitely are is the concept that allowed us to get over the paradox of the tangent velocity problem that we outlined last time. So the thing that students and non-students alike get confused about with limits is what makes them different than just a function taking on a value. So it is somewhat subtle, but I want to take some time to explain it as best I can. So what makes a limit different is the difference between approaching or getting sufficiently close versus evaluating at a point. Okay, so I tend to think of things graphically, but if I have a function that's behaving in a specific way, and let's say I care about some value L here that it takes on in its output. Okay, and here's my f of x. So the difference between approaching and taking on this value, well, taking on this value would just be plugging in c, the x value, into this function and getting the output L. Difference of approaching is saying, as I take some x values and head towards c, what is my function heading toward? And maybe if I take some x values just above c and I approach c with them, where is my function heading? Okay, so this is a very different notion. It's our best guess of where a function is going. So if you think about limit, it's like the limit of a behavior or the limit of some ongoing process. It's where is it tending toward? Tending toward. To have a limit exist, we say that it converges. So it's really converging or coming to a certain point or a certain value. It's not, blasting off to infinity if the limit exists. And again, this is a very different idea than just having a function take on the value. So I think we overplay in calculus things having holes. It is a key problem, but really, most functions we care about are continuous. They do go where they say they're going. But we have to understand this idea of approaching versus being there, okay? So I want you to kind of mull that over in your head of like, what's the difference between walking towards something and actually being at a point? All right. So from a graphical numerical perspective is probably the easiest way to think about this at first. So let's consider the simple function f of x equals x squared, the parabola. The limit, or what f of x approaches as x approaches 2 is shown by this table down here. So what do we see? How do I approach a value x equals 2 to see what's happening with a table? Well, I'd start with plugging in values like 1.9, 1.99, 1.999. You see how we're getting closer and closer to 2? And then see what the output says. The output's 3.61, 3.96, 3.996. Seems like it's getting closer and closer to the value 4 without hitting it, right? And in the same way, if I look at coming at it from the right, 2.1 is larger than 2, right? So it'd be like coming from this direction. Larger than 2, 2.01, getting slightly closer to 2 from the right, 2.001, and then seeing what the output of the function tells us, 4.41, 4.04, 4.004. It appears that f of x is approaching 4 as x approaches 2. That little arrow means like approaching. So from a numerical perspective, we can explore this idea of approaching. Again, f of 2 is 4. That is not what we're talking about. What we're talking about is how do we tell that something is approaching a certain value and that doesn't magically just pop into the value 4 when it is elsewhere for other inputs. Okay. Another way to confirm this is by looking at a graph. You look at the graph of f of x equals x squared, and you take a look what's happening at x equals 2 here, and we see that in fact if I move along this axis with my inputs, my function will follow along this curve heading towards a height of 4. If I come in at 2.1, 2.01, 2.001, my output responds by getting closer and closer to a height of 4 near those inputs. Okay, so this is two ways of looking at the same idea of approaching. So you might recall from pre-calc that we had this notation that f of x approaches L as x approaches C. This was both in the long run and at single points. For our example here, we said that x squared approaches 4 as x approaches 2. And so now we're just going to upgrade this notation to be more in alignment with what we use in calculus. So instead of saying this like we used to, we're going to use this notation. Okay? And what this says, how we read this, is the limit as x approaches C of f of x is the value y equals L. It's a value for the output to be approaching. Okay, so that's why I put the y equals in there. So the limit as x approaches C, and maybe I'll even put in here, as x approaches x equals C, of f of x is y equals L. So the output seems to be heading towards this value L as the x input is getting closer and closer to this value C. Now, this is a very informal definition, but it's going to be good enough for our purposes for right now. So let's look at an example. This actually comes up a lot in signal processing. This is called the sinc function, S-I-N-C, for those of you going into that field. But at any rate, it's a famous limit as we let, this shouldn't be x here, I have a typo in my notes, it should be theta. As theta approaches 0, what does this sinc function, sine theta over theta, do? Well, we see we have a problem in that we're letting theta go to 0, but theta is in the denominator of this function, right? So here's where it really matters about approaching versus being, because this isn't defined at theta equals 0. Undefined at theta equals 0. Again, why? Can't divide by 0. Right? So, but we can talk about where it's heading toward. Okay, where is it heading toward? And if we look at a graph or we look at a table and we let theta come towards 0, from the left we see the output of this function heads up here, and as we approach it from the right, 0.1, 0.01, etc., we see it's approaching this value from the left, and it's approaching this value of y equals 1. So again, we can confirm this or have a suspicion of it graphically. We can get a better job of confirming it with using a table. And then there's also ways to do this algebraically, but this particular limit, we can't do that until we're a little bit later into the course, actually. But a way to represent this limit using this notation, we'd say that the limit as theta approaches 0 of sine of theta over theta equals 1. All right, and this is an important one to commit to memory, and we know this via the graph and a table, and I'd actually encourage you to do this on a table yourself. You plug this into your Y1 in your TI-84 or whatever device you have, and then let the input values get closer and closer to 0, like we did up here, getting closer and closer to 2. Okay, another concept that's important is that of a one-sided limit. You've seen me approach these values from both sides of the input, but sometimes that's not possible. Sometimes we'll have a break in a function or we only care about approaching from one direction. Maybe negative time doesn't make sense, so we're approaching 0 time just from, positive time values, things like this. So the idea of the limit actually, okay, my wild gesturing got the best of me again. So the idea of a one-sided limit means that you can come at something, approach something from one side, and then we can change what a limit really means by including both one-sided limits. Okay, so we can split it into 2 approaches, and then what we say is, in this other way to understand limits, is that the limit of a function exists if the limit from the left equals the limit from the right. Okay, so are they going to the same place? Then that means we have agreement. That means we have convergence. All right, and we use this notation, this superscript of minus and plus, which might seem really weird. It's not an exponent, it's just a superscript. What this says is that as x approaches c from the left, f of x approaches L minus, which is just some number, and vice versa for this here. It's approaching from the right. So again, this was like our 2.1, 2.01, and this is like our 1.9, 1.99, etc. So we want to see, are they pointing to the same place as we approach from both sides? So here with this like step function we've got, let's take a look at the function at the point x equals 2 and see what's going on here. So this is a little weird actually. This should probably be open-ended here and here. Not sure what happened with the graphing utility. But anywho, if we look at this x equals 2, as we approach from the left, right? As x approaches, let me write this a little bit bigger down here. As x approaches 2 from the left, this one-sided limit of f of x, which I don't have the formula for, but I can just go by the graph. What is f of x approaching? Well, it seems to be approaching the value 1.5 if we approach it from the left. But if we approach it from the right, 2.1, 2.001, the limit as x approaches 2 from the right of f of x, well, this is a different value, right? I'm coming from the right, and I'm seeing these outputs up here, and I'm approaching this value, which is what? 2.5. Okay, so we'd say that this is, this is our left-hand limit. We'd say this is our right-hand limit. And so if we asked, does f of x have a limit at x equals 2, we would say no, since the limit from the left doesn't equal the limit from the right. We'd have to cite this work here. But we know that these are not going to the same place, so we can't say that the limit exists, that it is going towards some value. So this is kind of like, a step function, like a silly example would be like at the post office. Once your package weighs 2 or more ounces, now it's the next price, right? It's this fixed thing. So it's not this smooth transition between the two. But this is an example of where we can have a break in what we'd say, all right, this isn't approaching the same value, so that limit does not, in fact, exist. Okay, so most functions, the functions that we play with on a regular basis, they're nicely behaved. So they go where they're approaching, right? Where they approach at any given point, it also takes on that value, and there's not a big problem. But there are some functions that get a little weird, that aren't as well behaved. And so here's a couple examples of them. Okay, so y equals 1 over sine of 1 over x as x gets closer and closer to 0. Or we could write this as, what is the limit as x approaches 0 of sine of 1 over x? Okay, so if we graph this thing, and again, make sure you're in radians mode, for this on whatever tool you're using. If we graph this thing, we see that as we get closer and closer to 0, right, we know that inside the sine term, if this goes to 0, it blows up. So it's definitely not continuous there. But the manner in which the limit doesn't exist is because it's oscillating back and forth faster and faster and faster. If you remember the sine function, what goes inside dictates the frequency, or how frequently that bounce happens. So when that number gets smaller and smaller and smaller in the denominator, that means the number inside this is getting bigger and bigger and bigger, right? I should have been highlighting here. So as this number gets smaller and smaller, this whole thing is getting gigantic. And so the frequency is becoming infinitely fast. So this is a way in which it's not converging to a single value. It's actually diverging. Okay, so that's what we would say here. We'd say this does not exist. It's an oscillatory discontinuity is something we could say. So DNE means does not exist. I'll say just as a cautionary thing that a lot of students will say a limit doesn't exist just when there's a discontinuity. But as we've seen, like over here, this limit does exist even though it's undefined here. So if I plugged in theta equals 0, I'd get it undefined. But the limit actually, it is tending towards 1. So we need to be careful about that. But this limit doesn't exist because of its oscillatory nature. For y equals 1 over x squared, let's explore the limit as x approaches 0 of the function y 1 over x squared. And here we are with this graph of y equals 1 over x squared, and we see that as we get closer and closer to 0 with x, that this blasts off to infinity. So we say that this blows up or goes to infinity. Oh, I need to be showing you my graph here. Sorry about that. So we say when we look at this graph, we see that on both sides it's blasting off to infinity. So we can do a little bit of justice here. Let's pull this in. So we can say that the limit doesn't exist, but we also will say that the limit is equal to positive infinity. I'll put this in air quotes. We'd say that it diverges to positive infinity, because this gives us an indication that both tails are heading in the same direction. This isn't a break where maybe a function's heading in two completely different directions. Okay, but this is what we when we say something, 1 over x squared blows up at x equals 0. Another way to frame this. All right, and lastly, you've got this function x minus 2 absolute value over x minus 2 as x approaches 2. So again, we're going to translate this into, let's see, does the limit exist as x approaches 2 of x minus 2 over x minus 2? Well, if you didn't see it from the algebra, we know that the top is always positive, and the bottom can in fact take on negative values. And so there's going to be this kind of hard switch when we hit x equals 2, that the bottom will make the whole thing negative since the top is always positive. And so you get this, what we call this jump discontinuity or step discontinuity here at x equals 2. So here's where we say, right, the limit from the right is not equal to the limit from the left. So here we could say, this doesn't exist. We wouldn't even put the equal sign in there because that doesn't make sense. We'd say this limit doesn't exist. We could say the limit from the left doesn't equal the limit from the right. There is a jump discontinuity. So these are kind of the main types of cases where a limit would break down. Okay, so last thing for this overview is just to show you this visualization I have here that will show, it's on a loop, and let's say we've got the function y equals e to the negative x. Okay, for y equals e to the negative x, it's a exponential decay. And so what we're saying is, does this limit exist as x approaches 1 from both sides? Does it approach e to the minus 1? And you can see what the left-hand limit and the right-hand limit are doing as we approach x equals 1 from both sides. And we can say, yes, in fact, the limit of this function does equal e to the minus 1. Okay, because it's a smooth, function with no breaks. Graphically, we can see it. Numerically, we can see it. And again, later we'll show through the laws of limits and continuity how we can demonstrate this algebraically, which is a much stronger way to prove that a function is going where we think it's going. All right, so that's it for this overview and this basic notation video, and we'll have some worked examples following this up.